Okay, we're back to finish up talking about simple harmonic motion by discussing pendulums. I'll talk about what the small angles only thing means towards the end of the video. But as far as a pendulum goes, it's pretty straightforward. You've all seen pendulums. You can all probably describe what a pendulum is. So let's say here's a ceiling, here's an anchor point. Now I have a pendulum, which just consists of a string with a mass attached. That mass is actually called the bob, the pendulum bob. And let's say that normally it would hang straight down. Let's say I pull it back to here. We're going to call this position A. If I were to let go, the pendulum will swing down through a low point and then back up to a certain height, and then it'll swing back towards A, and it will keep doing that. Again, we're going to assume that there is no friction, okay? No damping. So, the pendulum will trace out a circular path. It will pass through positions such as B, C, D, and E. And just like we did for the springs, both vertical and horizontal, what we're going to do is we're going to look at the different variables that are associated with all these different positions, and we're going to analyze them and see how they change as this pendulum bob moves in simple harmonic motion. So we're going to have A. We're going to take a look at the X and Y positions. We're going to take a look at the velocity, or speed, I should say. We're going to take a look at the acceleration, the kinetic energy, the gravitational potential energy, and the size of the restoring force. Let's assume that the origin is at position C when the pendulum is at, and that's also the equilibrium position. And again, we're assuming ET equals ET. So let's assume that equilibrium, that the origin is at the equilibrium position. That would mean that at point A, this is as far to the left, or as far in the negative x direction as this pendulum will get. So we're going to call this the negative max. Okay? The x position is at a negative and it's maximum. The y position, on the other hand, is as high as it gets, so that is at a maximum. Since it's the point where the pendulum is dropped from, that means that the speed at this point is 0, which means the kinetic energy is 0. Since the y variable, since the height is at a maximum, the gravitational potential energy is also at a maximum. And as far as the acceleration goes, remember that one of the definitions of simple harmonic motion is that the restoring force is proportional to displacement. Just like the force was biggest when the object on the spring was as far from equilibrium as possible, that's the same thing is going to be true of a pendulum. The force, the restoring force, is going to be as big as possible when the displacement is at a maximum, which we do have here. So that means that the restoring force is going to be at a maximum, and it's going to be directed towards equilibrium here, so it's at a positive maximum here for the restoring force. And since Newton's second law says F net equals ma, if the force is at a maximum, the acceleration is at a maximum as well, a positive maximum. Now I could list out everything for B, but I'm actually going to skip B for just a moment, and we're going to skip right over to C, and then we'll come back and take a look at B. Because B, as you can see, is kind of an intermediate state. It's not all the way up at the turning point, it's not down at equilibrium, it's kind of in the middle. We're going to skip that for right now and look at C instead. At equilibrium, we know that the x position would be 0 because that's the origin, and the y position is also 0 because it's at the origin. Since the y position is 0, there is no gravitational potential energy because there's no height. Since it's at the origin, or since it's at equilibrium at position C, that means that the forces are balanced. I suppose you could say that there's a tension force pointing up, which contributes to a centripetal force, and a force of gravity pointing down still. So you could say that there's a net force directed up, but that's not the force that I guess I would say is causing the simple harmonic motion of this. That those forces aren't directed in the direction of the object's motion. So therefore we wouldn't really refer to either of those at this point as restoring forces. So the restoring force is actually 0, and I'll just put a little note that this is 0 tangent to the object's motion. And if the force is 0, then the acceleration is also 0. We're left to talk about the velocity and kinetic energy. If you can picture a pendulum, you know that it accelerates from its high point down through equilibrium and then slows down. That means that here, since the acceleration is 0, it's neither speeding up nor slowing down. It's sped up previously, before that, from A to C, so the velocity must be at a maximum here, or the speed, I should say, which means the kinetic energy is also at a maximum. Now let's go back and fill in B. We're just going to talk about how these characteristics are changing on the way from A to C. Well, the position X, we can tell, is increasing because it's negative still, but it's going from the maximum negative position, or X position, to 0, where the equilibrium and origin is. So I'm going to say that the position is greater than it is at A. The Y position is less than it is at A because it's going down. The velocity, we know that the velocity is, or the speed, excuse me, is increasing. So I'm going to say that it is greater than A, greater than it is at position A. The acceleration is decreasing. It's not as big as it is at A. And this would actually be a good point because I haven't really mentioned this yet. When we talk, well, when I get to the force, I'll mention it. The kinetic energy would be the same as the velocity. It is greater than it is at A. Gravitational potential energy is the same as it is proportional to the height, so that's decreasing, less than it is at A. And the force is proportional to the acceleration, which means it is less than it is at A. So what we're talking about with the force, I mentioned in the first video that the restoring force for a pendulum in simple harmonic motion is a component of the force of gravity. It's a component. It's not the entire thing. The reason it's not the entire thing is if you think about the force of gravity, it is always directed straight down in situations like this. However, the pendulum is not going to move straight down. The pendulum is going to move kind of down and to the right. So we could break this force of gravity up into components. I have a component that is in the direction of motion, and I have a component that is perpendicular to that direction. This component right here does not fit the definition of simple harmonic motion. It is not directed opposite the displacement, okay? However, it's 90 degrees from the displacement. The displacement is kind of up and to the left. This is down and to the left. That's 90 degrees. It's not going to affect it. However, this component right here is, in fact, directed opposite the displacement. The displacement is up in this direction. This is directed down and to the right. This is the component that we care about. And if you think about it, as we continue to draw this component, as this pendulum swings back closer to C, that component is going to get less and less. Because right here, at position C, the object, if it started at A and moves this way initially, it's going to be the object's velocity is directed to the right. The force of gravity is down. No component of the force of gravity is in the direction or opposite the direction of motion. So that means there's no restoring force at equilibrium from this component, which is exactly what the definition of a restoring force is. Should be no restoring force when the object is passing through equilibrium. So this is the component of the force of gravity that we care about in terms of the restoring force. Okay? That's why we say a restoring force is a component of the force of gravity. D and E are very similar to B and A. Again, I will do E first, then go back to do D. At position E, the X variable, the horizontal position, is at its positive maximum. The Y position is also at its positive maximum. Let's make sure you can see that there. Okay. Since this is the highest the pendulum goes before it is the turning point, it's where it turns around. It's not going higher, but it hasn't dropped any yet. That means the velocity must be 0, which means the kinetic energy is 0. The gravitational potential energy is proportional to the height, so that is at a positive maximum. And if we think about it, the restoring force should point back towards point C, so it's negative. And this is as far as the pendulum goes, so it's also at a maximum, which means the acceleration is also negative and at a maximum. And as far as D goes, again, we're just going to compare this to position E. We could also compare it to position C, but just for the sake of being uniform, we'll compare it just to position E. The X position is less than it is at E. The y position is less than it is at E as well. It's not quite as high up. The speed is greater than it is at E. The acceleration is less than it is at E. The kinetic energy, since the velocity is smaller at E, or the kinetic energy, excuse me, is greater than it is at E. The gravitational potential energy is less than it is at E. And the acceleration is less than it is at E. Again, an AP question is not going to ask you to set up a table like this. An AP question is going to ask, do you understand how these variables change as time goes on? Can you point out a graph of how the kinetic energy changes from A through E? Can you explain why the acceleration is greater at E than it is at D? Things of that sort of nature. We like to talk about, just like with the springs, we need to talk about the factors that might affect the period of the pendulum, just like we talked about factors that affect the period of the spring and mass system. There might be, so if we look at this, you might say, okay, well, perhaps length is one of those factors. Hopefully at some point you've all seen a grandfather clock. If you change the length of that pendulum that ticks in the body of it, it'll change how fast it moves, the arm moves. Perhaps the mass of the pendulum bob has some effect to it. Maybe the release angle has some effect to it, okay, how much you bring it back. As a matter of fact, that one does, but we do have to make a note about that. So when we talk about pendulum and we talk about small angles only, I'm going to add a note, excuse me, I'm going to add a note to the top here. When we discuss a pendulum, the angle of displacement, okay, this angle right here, the angle from the straight line down to what the maximum angle that the string makes, has to be under about 30 degrees. If you have larger angles, so for instance, this is much greater than 30 degrees, this isn't really what we're going to be studying. For larger angles, not a perfect example of simple harmonic motion. Okay? All of these are still true, but the equation that we're going to derive, I'm not going to tell you what the equation is right now. The equation only works if we're dealing with an angle under about 30 degrees. Okay? Again, we're going to find the equation through an experiment in class, but the equation itself only works if your initial displacement angle is under about 30 degrees. By the way, limiting it to under 30 degrees is known as the small angle approximation. Now, there is a reason for the small angle approximation. There's a reason why we do this. It's not super important to really get into. If you really want to know, you can look it up. The essence of it is that the displacement, the angular displacement theta, is not quite proportional to the restoring force, I believe. The restoring force is proportional to actually the sine of the angle, like the sine, the trig function. But it turns out that mathematically, when you take the sine of an angle and you compare it to that angle in radians, those numbers are almost the same as long as you're under about 30 degrees. After 30 degrees, they start to diverge quite a bit. So that's what the small angle approximation is and why we use it and why we say that pendulums are approximately simple harmonic motion if you're under this initial angular displacement. Not super important that you know exactly why, but just keep in the back of your head that if you are using a pendulum, and let's say you want to use the equation that we're going to learn for the period of a pendulum, if you bring the pendulum back more than about 30 degrees, you're not going to get very good results. We'll do this part in class, the actual equation. To sum up for this video, what I want to do is just kind of talk in general. Let's look at these quantities. How are they related to, or how do they change for an object in simple harmonic motion in terms of where the equilibrium is and where the maximum and minimum positions are? So let's start off with position. We, in every single one of these scenarios, said that the equilibrium position is the 0 position. Okay, that's where the object, I wouldn't say necessarily starts from, but that's where we usually say x or y are 0. And the turning points of the object, or of the system, where it reverses course and goes back towards equilibrium, those are the maximum and minimum parts. In other words, when the object gets too high or gets too far to the left or to the right, or object gets too low, that's where the turning point is, okay, at those maximum and minimum positions. For velocity, if you go back, and I encourage you, go back and look at your notes and what we've written down here. When we have the velocity at a maximum, it's always at equilibrium. The velocity is always highest at equilibrium. And again, that makes sense because equilibrium is where the forces are balanced. If there's no force on an object, that means, or if there's no net force on an object, I should say, that means that there is no acceleration. And if the object's been speeding up until that point and there's no acceleration, then that means that the object is moving at its fastest speed. As soon as the object moves past equilibrium, it starts to have an acceleration back towards equilibrium, which means it's going to start slowing down, and it's going to slow down until it hits the turning point, at which point it reverses direction, accelerates towards the equilibrium, and it's moving towards the equilibrium, so it picks up speed, and that continues on for forever until the system is stopped. So the velocity is highest at equilibrium, and it's 0 at the turning points. Okay, makes sense. Objects don't move at turning points. Okay, if an object was moving at the turning point, then that means that it wasn't a turning point. Either it's going to go farther or it's already coming back from the turning point. So objects do not move when they reach their turning points in simple harmonic motion. Acceleration. It's 0 at equilibrium. Equilibrium is where the forces are balanced. If forces are balanced, that means the net force is 0, which means the acceleration is 0. It is highest at the turning points. This is where the restoring force is at a maximum, which makes sense because the restoring force increases the more the object has been displaced. And at the turning points, that's the maximum, displacement from equilibrium. Kinetic energy. Kinetic energy, since it's 1/2 mv squared, goes right along with velocity. This is going to be highest at equilibrium because the object is moving the fastest there. And it's going to be 0 at the turning points because the object isn't moving. Potential energy, and I'm going to make a note about this one. This is for, so I guess I'll say, except for the vertical spring. The potential energy is 0 at equilibrium. And it's the highest at the turning points. I guess you can't really say that that's the case for a vertical spring because the object is moving fastest. It is moving fastest at equilibrium for sure, which means the kinetic energy is accurate. But as far as the potential energy goes, I wouldn't say the potential energy is 0 at equilibrium for a vertically hanging spring with a mass attached. The gravitational potential energy, again, you could really set the 0 of the gravitational potential energy to be anywhere, as we know. I set it at the bottom, so it's kind of 0 at the bottom, but it keeps increasing the gravitational potential energy the higher you go up. And the elastic potential energy would be 0 when the spring is unstretched, which is kind of like at the top, but it's not really defined if the spring is unstretched or just a little bit stretched up there. So with a vertical spring, it's a little bit different, but you still should be able to figure out what's happening. Essentially, the elastic potential energy will increase as the spring stretches more. The gravitational potential energy will increase as the object gains height. That's easy enough to know. And finally, the restoring force is proportional to the acceleration. So that means that it is 0 at equilibrium because the forces are balanced. And it is highest at the turning points where the restoring force is the greatest. That's pretty much it for simple harmonic motion. We'll go through a bunch of examples. We'll do some really good labs in this unit. Your job right now should be continuing to familiarize yourself and understanding as we go through these demonstrations and tutorials, okay, well, how are these factors changing? Again, we're going to fill in the equations for period of a mass and spring system and period of a pendulum as we go in class and figure those out. But really what I want you to be thinking about is how are all these variables changing as an object goes through its simple harmonic motion. That's it for right now. I will see you for the next unit.